Good morning from Dhaka, Bangladesh. This is the third lecture of the lecture series I'm preparing. The last slides of the second lecture was this one. I take it again to let you know this is very important to write electronic configuration. We have to know the energy level, and we also know that electrons go first in the lower energy level and then fill it up and according to higher energy. So these three picture I showed is one about principal quantum numbers and number of subshell we can have from each principal quantum number. And then this one, we show how the energy increases in various subshell. Thereby, we know which or the energy level will be filled first and then next and next one. It may happen to you that it is a bit complicated, but a very simple diagram I draw here, which is that I know principal number 1 has got only one orbital. Similarly, principal number 2 has got 2 orbital, 3 has got 3 orbital, 4 orbital, 5 orbital, 6 orbital, and 7 orbital. But I didn't show you 6 orbitals of 6 energy level or 5 orbitals of 6 energy level all. Only 1, 2, or 3. Why? Because we have 118 elements, and if we want to write down the electronic configuration, we need that's up to 5d orbital or 6s orbital or 7s orbital, and rest 4f is only. So this might be a bit complicated for you, but in this figure, if you remember, then you can say, if you draw like this, then we have to fill the first 1s orbital, then 2s orbital, and then 2p 3s, and then 3p 4s, and then 3d 4p 5s, and so on. So this is a simple diagram which you need not to memorize. Simply write it, and then you can find out which orbital to be filled first for the electronic configuration. I go to the next slide. This lecture, what I'll do, I'll solve few problems in the last lecture we discussed, and then a set of rules to be followed for writing electronic configuration. And then we talk about shapes of s and p orbitals, and then we talk about experimental evidence of electronic configuration of atoms, and then we talk ionization energy of elements, and few problems on today's discussion. If time permits, I'll continue discussing another topic, periodic table. We go for the problems. We had a problem in the last, or we could say we have problem. So how many protons, neutrons, and electrons are there in the following atoms and atoms? Atom is this: uranium, beryllium, calcium ion, and potassium ion. You see, we have to find it out if we do know the proton number of each of this. That is atomic number we must have to know. Now you might ask me, where do we get atomic number? In the periodic table, we get atomic number. So you may ask, where do I get periodic table? Periodic table is allowed in your exam hall. Periodic table is always allowed in your class. So you can get proton number from periodic table of each and every 118 elements. So here the proton number, this means atomic number of uranium is 92. And this is the mass number. Therefore, proton number and electron number are same unless this element becomes ion. So here we write 92. Proton number is 92, electron number is 92. Now the neutron number, we have to subtract subtract atomic number from the mass number, and we get neutron number. Here it is the neutron number. Similarly, we go for beryllium. Now we are coming to cation. That means calcium 2 ions. Whenever it is a cation, we have lose electrons from the neutral atom. So here the proton number is 20, and if we subtract proton number from mass number, then it is neutron number 20. And since we had 20 proton and we have also 20 electron, now that is, it is a cation and 2 plus, therefore we lost 2 electron from here. So for this cation, it is electron number is 18. Similarly, we go for potassium, we will see the electron number is 18, proton number is 90, and from proton number, from mass number, if we subtract proton number, we get neutron number 20. So it's easy. So these type of question you get in your A-level exam. Another question is that we know relative atomic mass of all elements. And you may again ask me, where do you get it? It is in the periodic table, and if not, in the question, you will be given relative atomic masses. So here in question, the relative atomic mass of carbon, iron, hydrogen, oxygen, sodium are given. Then you are asked to calculate the mass of the following: 0.2 moles of carbon dioxide, 0.05 moles of sodium carbonate, and 5 moles of iron hydroxide. What is to do first? First of all, we have to find out the molecular mass, relative molecular mass. And how do you do it? So we take the relative atomic mass of each atom of the compound, and that add it up, and it becomes the relative molecular mass of that compound. So in this case, we have done it, and how it is that we get for carbon dioxide relative molecular mass 44, for sodium carbonate relative molecular mass 106, and for iron hydroxide it is 89.8. Now your question was that calculate the mass of this mole of carbon dioxide. So we know mole is equal to mass of the substance in gram and divide it by molar mass of the substance in gram per mole. So here 0.2 moles of carbon dioxide means that the molar mass is 44. So we multiply this 44 into 0.2 and we get immediately the mass of 0.2 moles of carbon dioxide, and it is 8.8 gram. And you go it like this for others. So it is. Now we go for the next slide. As I said about atomic number, mass number, we get it from periodic table. I say here is a modern periodic table of all 118 elements. Now, I will talk about this periodic table in next lecture, how periodic table is developed and what are the information we get from the periodic tables. That will be my next lecture. So this problem was also in the last second lecture's content. Again, use the relative atomic mass of following elements: iron, nitrogen, oxygen, sulfur, and then we have to calculate the amount of mole in each of the following. What is given here? It is given the sulfur's mass, that is 10.7 gram of sulfur. Similarly, 62.8 gram of sulfur 8 molecules. And the third one, 60.45 grams of ferric nitrate, that is nitrogen 3, iron 3 nitrate. Okay, so as usual, we find out the molar mass of sulfur, and then sulfur 8 molecules, and iron nitrate. And then what we do, we simply divide this gram given to us by molar mass, and we get the number of moles. We are asked to calculate the number of moles. So here 10.7 gram of sulfur, and the molar mass of sulfur is 32.1, and we just take 10.7 gram divided by 32.1 gram per mole, and we get 0.33 mole. Now we go for sulfur 8 molecules. So we have to find out the molar mass of sulfur 8 molecules. That means 32.1 into 8. And then just divide this with the gram given to sulfur 8 molecules, and we get the mass. There it is, mole. That is 0.25 mole. I'm sorry for that. And then about ferric nitrate, we take the molar mass of ferric nitrate as we did others, and then divide this gram by molar mass of nitrate, and we find out that the mole of ferric nitrate is 0.31. Another question was that use the value of Avogadro constant. This constant is given here, 6.02 into 10 to the power 23 per mole. And then we are asked to calculate the total number of atoms in 7.1 gram of chlorine atoms. That means we have to find out how many atoms we have here. So what we have to do, first we have to find out the number of moles of chlorine atoms in 7.10 gram. That we have done now. It is 0.2 mole. As we have said, Avogadro constant is 6.02 into 10 to the power 23 per mole. This is the number. So we have 0.2 mole, and then therefore number of atoms in 0.2 mole of chlorine. What we do, here we have some mistake. You see? It is not 0.2, it is 0.2. Sorry. Yeah, it should be 0.2. Okay. So 6.02 into 0.2 into 10 to the power 23. The result coming up will be number of atoms in 0.2 moles of chlorine. The last question, we have been talking about the principal quantum number, azimuthal quantum number, magnetic quantum number, magnetic spin quantum number. We are saying that a set of these 4 quantum numbers specify the electron in space, or specify the probability of finding electron in space, and that is what we call orbital. So what do you mean by a set of 4 quantum numbers? We have to give a value of each quantum number. And we have to give a value of M, L, ML, and MS. So there we have 1. So if N is 5, then principal quantum number is equal to 5. And the azimuthal quantum number, one of the azimuthal quantum number, if N is equal to 5, is L is equal to 0. Then magnetic quantum number, of course, it is also 0. And then magnetic spin quantum number value is either plus half or minus half. So we give plus half here, and this is one of the sets of 4 quantum numbers when N is equal to 5. Okay, we go to similarly, you can find out number of set of quantum numbers when N is equal to 5. What you have to do, you have to find out the allowed all values of azimuthal quantum number, allowed all values of magnetic quantum number, and values of one of the 2 values of magnetic spin quantum number. And I say it again, this is for the probability of finding electrons in orbit. Okay, I said this today we will talk about a set of rules to follow for writing the electronic configuration. And these are, we have to know the atomic number of the given atom whose electronic configuration to be written. So this is Z, and I said a few minutes ago, we get from the periodic table Z of any elements we want. Then we have another principle, we call it Aufbau principle. And Aufbau is German word, which in English it is building up, and in most English book you will get it building up principle. But the scientist who did first, he said Aufbau principle because he was a German. And what did he say? Electrons go into the orbital with the lowest energy, available energy level first, and then higher and higher values. I showed in the beginning the energy values of the shell and subshell. We have to remember that, and we don't need to memorize it. Energy levels of orbitals of different shell and subshells are experimentally determined and known. We know it. Another principle, call it Pauli exclusion principle. Now we're coming to the set. No two electrons in an atom can have the identical set of 4 quantum number. That is the Pauli exclusion principle. If we tell it in another language, what you can say, each orbital can have a maximum of 2 electrons with opposite spin. So now we know that every orbital will have a maximum of 2 electrons, not more than that. And then we have Hund's rule. What it says, if we have 2 or more orbitals in same energy level, then electron fields in every orbital singly with same spin before it pairs with another electron with opposite spin. This arrangement is called electronic configuration also, and it is also called electronic boxes. Here I would like to ask you, do not forget that if you do not follow any of these principles, your electronic configuration representation will be wrong, totally wrong. The electronic configuration, I have given few examples of electronic configuration written in 1s, 2s in this manner, in this convention. I have given 3 electronic configuration here, and I said these are not correct. Why? Next question is why. The first one we write 1s2, 2s2, then 2p5, and then 3s1. Did we follow Aufbau principle here? No, because 2p has got lower energy than 3s. So we have to fill up 2p first, and 2p can accommodate 6 electrons. Therefore, this representation of electronic configuration is wrong. Do remember it. And then we have another one, 1s2, 2s2, 2p7, 3s1. As you see, it cannot be, because according to Pauli exclusion principle, each orbital can have maximum of 2 electrons. So 2p has got 3 orbitals, therefore it must have 6 electrons, not 7 electrons. We cannot do it. So this is a violation of Pauli exclusion principle. And then we go for the next one, 1s2, 2s2, 2p6, 4s1. Why do you get wrong? Why it is incorrect? Because we have not filled the 3s, 3p. Because 3s, 3p is having lower energy than that of 4s1. So that one also violated Aufbau principle. Okay, another one, the question is, we have electronic configuration of atoms. 3 electronic configuration has been given here. You see, 1, 2, 3. And then we were asked name the atoms whose electronic configuration are these. Well, you count the electron number. An electron number is equal to proton number. Go to periodic table and you immediately get who's the name of the atoms. Is it not? So here we have 10 electrons. No, 10 electrons. Is it? So 6, 10. So it should be 10, not 8. Z is equal to 10. And then here it is 12, and then it is 13. So we have to go to periodic table and find out what is 10 means, and what is 12 means, and what is 13 means. Well, why 2p have 6 electrons? You know that whenever we have subshell 2p, there we get magnetic quantum number 3 for L is equal to 0, 1, and minus 1, 0, plus 1 in this case. So we have 3 orbitals, and we designate it as px, py, pz. So 2px, 2py, 2pz. So each orbital can accommodate only 2 electrons as per Pauli exclusion principle. Therefore, 2p must have 6 electrons because it has got 3 orbitals. Next slide. We say there are many conventions to write electronic configuration. One is, as I said, 1s2, 2s2, etc. And another one, a shortened version, that we have a noble gas core. And noble gases are helium, neon, argon, krypton. So if we write noble gas core, like third bracket, and then rest electrons. We take an example. The oxygen has got this electronic configuration 1s2, 2s2, 2p4. If we go for this version, we write the electronic configuration of oxygen like this. The simpler version, because 1s2, 2s2 is the electronic configuration of helium. So we write in third bracket helium, and then 2s2, 2p4. 1s2 is the electronic configuration of helium. And therefore, for the simpler version, we just write that in third bracket, the noble gas core, helium, and then rest of the electrons, 2s2, 2p4. This is a simpler version of writing electronic configuration. Similarly, if we go for magnesium, 1s2, 2s2, 2p6. And this is the electronic configuration of neon, a noble gas. So we write the electronic configuration of neon and then rest electron 3s2. This is how we go for. And for this one also this. Here is a electron in boxes diagram. If you remember, we said if there are more than one orbital, 2 or more orbitals in same energy level. 2p is the same energy level, 2p, and that has got 3 orbitals. So electron, we have to fill first in same spin in every orbital 1. And then if we have more electrons, we will come back and pair it, which we have done here. So this is for helium, electron in boxes. This is for nitrogen, electron in boxes. This is for sodium, electron in boxes. I think our time is over. So this is the third lecture on atomic structure. And we will finish it up in the next lecture, the third one. And probably we take also another part of another lecture, the periodic table. So thank you all. Well, sorry. When I showed electron in boxes diagram, and I said it helium and neon, helium, nitrogen, sodium. So helium electronic configuration is 1s2, hydrogen and then helium. So Here, it's a mistake to show this one 2s2. This should be vacant. This should be vacant, like this one. Yeah, this is the wrong statement according to this figure. I correct it by taking away these two electrons, and then it is the electron inbox diagram of figure.